Last time we talked about vector fields, and one of the cases of a vector field that we were interested in was where, for example, you had multiple, say, planets or other celestial bodies, where the force due to gravity at every point, well, the direction and magnitude depend on where you are relative to both of these planets, so that, say, a point here might have a large vector mostly in this direction, whereas a point that's further away might have a small vector like this. So we model that with a vector field, say f of xy or f of xyz. And the problem we want to think about right now is a problem about work. So let's imagine now that you have an object that is moving, maybe it starts here and it moves along some path to there. And we want to know how much work that gravity does as your object moves from point A to point B. Okay, so how do we approach a problem like that? Well, first, it's useful to remember what the easy case is whenever you have a physical problem like this. So the easy case we talked about in the very beginning of the course. That's where you have a force vector that is constant and a displacement vector. So you have an object that moves in a straight line from one point to another under the presence of a constant force. And what we learned was that the work was the dot product of the force with the distance. Now, what we always do then with complicated things like this, where now the force isn't constant and now the path isn't a straight line, is we split it up and try to approximate it with nice pieces. So for example, this green path here, we could kind of approximate with a piecewise linear path. And along each of those pieces, well, I have all these little kind of sub-displacement vectors. So say I have a displacement vector from point A to this first point over here. And then what happens is that if that displacement is small enough, well, even though the force is different at the beginning of the path and at the end of that little path, the smaller the pieces, the less the force changes. And so I might just kind of squint and imagine that the force is constant. I'll sort of treat it as constant for the purpose of approximating. So what I might do is somewhere in the middle here, say right here, measure the force, and whatever force I get, use that as if it applied to the whole displacement. Okay, so this is the basic idea. We're going to, so we want to approximate the path with line segments. And treat the force as if it were constant on each piece. Okay, so we end up then with, say, these 2 points on my path that I connect up. And I have some force vector that I'm going to measure somewhere here in the middle. And I'll sort of move that vector and put it over here. And so you end up with some force at some particular point, some kind of displacement vector. And then what we would like to do is we'd say, well, let's add up all of those force vectors times distance vectors. Maybe you might call it force sub I, d sub I, where I goes from 1 up to n. And n is just the number of pieces that you've used. Okay, well, how do we actually do that? How do I kind of get my hands on this path and all of that? Well, what we're going to assume is that your path C is parameterized by some function r of t, where t ranges from a to b. And so then the idea is that you're going to take that range of t values from a to b, and you're going to do basically the same thing that we do in Calculus 1, which is you're going to split it up into a bunch of little pieces. So a we also will call t sub 0, t sub 1, t sub 2, all the way over to t sub n. And so what we're going to do is then, for the force, well, basically, say, if you wanted to find the first piece, f sub 1, what you would do is look at this first interval from t0 to t1. You'd plug some value in there into the parameterization r, and that gives you a point, and then you would measure the force at that point. So remember, we have that F is really given by a vector field, right? The force is F of x, y. But I can kind of think of that then as being F of r of t, because if I plug in a t value into r, I get an x coordinate and a y coordinate, and then I can plug that into F. So F sub I then is going to be something like F of r of t sub I. Right, so for example, I could just take t1, plug it into r to get a point, and plug that point into F to get a force vector. What about the displacement vector, di? Well, by definition, a displacement vector is a difference in positions. So it's going to be r of ti minus r of t sub I minus 1. Right, it's sort of a change in r values. But actually, what's going to be useful is to approximate this. And here we use a trick that we use all the time for this sort of calculus thing, where if I want a difference in r values, that's approximately the same as the derivative of r times the difference in t values, the difference in the inputs. And so what happens then is we end up with the sum from I equals 1 to n of f of r of t sub I, that was my force vector f sub I, dotted with r prime of t sub I, and then times delta t. And of course, really what I want, if I want the actual work, that should be the limit of that as n goes to infinity. And well, the inside here, all of the stuff, I mean, it looks fancy because it's a dot product of vectors. But a dot product of vectors is ultimately just an ordinary scalar function. And it's a function of t. And since I have a function of t times delta t, and I'm taking the limit as n goes to infinity, this then just becomes an ordinary single integral in terms of t. It's the integral from a to b, because that was the range of t values that we said before, of f of r of t dotted with r prime of t. And often we will write that a little bit more abbreviated as just f dotted with dr. Well, in fact, usually we don't even write the a to b there. What we'll write is the integral along c, where c was just the name of the path, of f dot dr. Okay, but this is just notation. This notation means to do this single variable integral here, and that single variable integral gives you the work that is done by this force vector field along the path c that is parameterized by r. Okay, so we'll see next time. We'll look at a couple of examples to see how this actually works out in practice.